time for J&P Technologies, a small business sub to the SAIC SNMA Flight Safety Office that supports the NASA JSC Flight Safety Office. And I might bring up here this, actually I got this presentation together because I had a request from SpaceX and the crew offices because in this commercial spacecraft we're getting ready to fly now, there's a high level of automation and very little or much lesser manual control than what's been used in the past spacecraft programs. And some years ago, when the commercial programs were starting to really get underway for crew override, with the Flight Safety Office, we developed, and I was the lead author of a request to investigate manual control and crew override and so forth. And so I'd like to start here. Let's see, you need to back up one slide.
Two.
Let's see, should be a slide 2. If not, I may have to pull up mine. Oh, here we go. Okay. And this just talks about this. Next slide, please. Slide 3. Here we go. This is important because I won't be bringing this up later, but if you're a designer and so forth, this is the things you need to consider before you even think about trying to put in a manual control. One, is the function critical for crew safety or mission? Is the time requirement to perform the function within the normal human response time and performance envelope due to automatic control system failure? In other words, when that system goes out, are you going to have the ability to do something? And this is a big concern of commercial aircraft as well. 3, is the crew monitoring of the automatic system sufficient to ensure they can seamlessly enter the control loop? Is sufficient information available to the crew to successfully perform the function? Are there sufficient controls or inhibits in place to preclude inadvertent engagement of this manual override capabilities? Next slide. And we'll have mission actual cases that pretty much indicate a lot of these later. Next slide. 6, is the crew trained and refreshed in the operation on a regular basis? Is the overall function reliability improved for crew safety and mission success with manual control? Take into account human reliability and mission duration impact. 8, this is the last item. Does the overall risk benefit trade support implementation of manual control override capabilities when you can take into consideration technical costs and schedule impacts for the program? Next slide, please. Next slide, please. Okay, Mercury program, the majority of the functions were manually controlled. Some critical functions such as emergency escape and flight control were automatic with the manual backup override. And the escape system for ascent could be initiated 3 ways: ground command receiver abort signal, astronaut abort handle, or the booster catastrophic failure detection system on the Atlas launcher. Retrograde rocket system, normal method was closing retrograde firing signal switch within the satellite clock. The switch could be activated by preset clock An astronaut could bypass this to start the sequence manually. Next slide, please. Next slide, please. There was also a capability to do an emergency override for the retro. You could push the fire retro button. And if you were not in this spacecraft correct attitude, you could do a manual fly-by-wire system to correct yourself. Fly-by-wire, the automatic stabilization control system was disabled. If you went into fly-by-wire and you actually had 28 volts connected to the limit switches on the control sticks that actually applied power to the valve solenoids. In addition, Mercury had something that you never see on other systems. It actually had another RCS control system that was strictly mechanical. You actually had mechanical linkages from the control handle that went out to the RCS control valves. Next slide, please. Next slide, please. Mercury 6 program, astronaut, this was John Glenn, took over manual fly-by-wire control for on-orbit entry when his yaw reaction jet caused an attitude control problem. And then later, during re-entry, because there was concern about the retro pack attached during entry, he had to keep that off. Mercury May 7 mission. We had a case where the automatic control system did not maneuver the capsule into the correct retro rocket attitude. Astronauts switched to a fly-by-wire, but failed to shut off the manual system. In other words, he ended up having both systems on. That ended up draining too much fuel. Crew error caused this excessive usage, and the depletion actually occurred at a higher altitude, 70 to 80,000 feet. And so his capsule started to swing. So he ended up deploying the drogue suits at a higher altitude in order to stabilize. And then he also had a crew error in yaw when he did the rocket firing that prevented the capsule from slowing down as much, and it actually overshot the planned landing area. MA9, when the automatic, oh, by the way, Cooper was on that, I mean, not Cooper, I'm sorry. Carpenter, I think it was. Carpenter on that flight never flew again after that mission, and having those many crew operated errors. MA9, when the automatic control system failed due to short, this was Cooper's flight. We had the complete electrical failure. So Gordon Cooper had to actually use that manual controlled linkage in order to come back home safely. Next slide, please. Next slide, please. Majority of Gemini spacecraft functions were manual controlled, but some were automatically controlled with manual backup. In this case, the malfunction detection system on the launch vehicle and so forth gave indications, but because on Gemini, the crew only had injection seats, you were only good up to about 70,000 feet. But they had, just like you had in the aircraft, they actually would pull a D-ring to start the ejection function if they had a problem. Next slide, please. Harness release actuator assembly. They installed it, and they had a system here. Of course, you had to get out of the seat. This was pretty much just like you had in the military when you're, after you'd already bailed out, and you had a drug mortar to fire and just stabilize you as you came down. And you had, and those were all manual functions. And next slide, please. Next slide, there we go. The OMS attitude maneuvering system was a bipropellant system. and two 95-pound thrusters, 8 23-pound control, and two 79 495 thrusters. And the control was either manual via the hand controller or automatic via the attitude control maneuver electronic system. And you had a primary and secondary system. And you had the capability to override the automatic system. Velocity control was along 3 axes, but there was no provisions for automated. It's strictly manual. Next slide, please. Reentry control system was a bipilot system and had 8 23-pound thrusters located in the RCS section between the reentry module cabin and the rendezvous recovery section. The crew could select between 2 completely independent reentry control rings, as they call it, ring A or ring B, and they had a direct bypass and could override the automatic system. Next slide, please. The retrograde rocket system had 4 solid propellant rockets. There was also a manual backup initiation capability for that. The Ascent Titan launch field guidance was the primary system for Ascent guidance, but for Gemini, the crew could manually switch to a Gemini computer for backup guidance of the launch vehicle for first and second stages. Next slide, please. I had 10 flights during the Gemini program. Gemini 4 had to perform a rolling manual reentry when the onboard computer failed. Gemini 5 had to take manual control to minimize a landing point error due to a computer programming error. And on Gemini 8, the commander had to manually select. This, by the way, was when Neil Armstrong was the commander on Gemini 8. He had to manually select for entry RCS system to regain spacecraft control, saving the spacecraft life. This is a case where they had been docked to the Agena capsule. In a lot of the training before, they were always concerned about the control system on the Agena. And so if anything came up, they were told to quickly kind of disendock from the Agena vehicle. All of a sudden, shortly after they were docked, they had started having firing, attitude problems and so forth. So they quickly did what they were programmed to do, is undock from the Agena, thinking, of course, that it was the Agena somehow. Instead, in this case, the Gemini spacecraft itself had a stuck-on thruster, and so you ended up spinning up the spacecraft much faster after you de-docked from the Agena. They were getting very close to blackout, but Neil quickly switched to the reentry system and stabilized the spacecraft, separated from that backstage, and they had to come home right away since they were on the reentry control system. That was a very close call for the crew. Next slide. Gemini 12, the backup manual capability was used for rendezvous when the automatic rendezvous motor failed due to problems with the OMS attitude control system. This was a flight that Buzz Aldrin was on. He was a rendezvous expert and written papers on it during his thesis and so forth. So actually, some of what he had on board was what allowed them to go ahead and do a manual rendezvous with the target vehicle. Next slide. Next slide. Yeah. Apollo. The majority of the Apollo functions were manual controlled. However, critical functions were automatic with manual crew backup override. Launch escape system and abort system, you had the emergency detection system in the Saturn launch vehicle. That could automatically abort you if you were outside the criteria. It was triple redundant, voted 2 out of 3 strings. If you had 2 votes, and by the way, the votes were an interruption of the power line. You actually had power routed 120 degrees apart, power in return from the command module that went all the way down to the Saturn IU. And there in the Saturn IU, you had relays such that whenever they got a signal to abort, they opened up that line. And the nice thing about that, by having that system in place, if you had a structural breakup of the launch vehicle, it would automatically initiate the abort. And that actually happened during a little Joe 2 launch for the abort system out in White Sands. I was there for that. But we actually had fin go hard over, vehicle spun around till the launch vehicle completely come apart. Because of that, broke the wires, it automatically caused the abort of the spacecraft and saved the spacecraft. Let's see here, somehow the chart got changed. Can we go to a full chart?
Hold on a minute.
Or I can go to share screen on my side and quickly catch up maybe. Okay, there we go. Next slide. The Earth landing system was automatic if the crew enabled it. It was designed to be that way. You had a system A and B. You could do all the functions required for the landing system. Reaction control system, command service module, they had 2 stabilization control systems. That's the automatic system for the control of RCS system A and system B. The crew could select controller power direct. You could go to RCS direct to either bus A or B, and the crew could control the CSM or command module attitude with that in controller. Next slide, please. Docking system. When you had 2 or 3 capture latches for soft capture, that would power up the panel switch to allow the crew to retract the probe. You've retracted the probe by firing a pyro, and that would bring the vehicle in to close contact, and you had structural latches that would automatically trip and dock you. So that was an all manual function. Service propulsion system was the main engine, of course, to do mid-course corrections, send your way onto the moon, and also bring you back from the moon. The crew had the capability to go from the automatic system normal to a direct on, so they could manually fire the SPS engine. It turns out during all of the Apollo missions, everything was done automatic, that we never did really have a case where the crew had to do a manual burn. Next slide, please. Lunar module primary guidance navigation control, called the ping system, was automatically controlled and landed the limb at the targeted landing area. The crew capability to switch to semi-automatic control and then manually control the landing. And as we know, Apollo 11 and most of the lunar crews ended up switching to manual control to do the final landing. Abort guidance system on the limb. When you were coming up from the moon, if there was a real problem, you could switch attitude hold, which was automatic, and go, the ag switch could be switched to ags and automatically try to rendezvous and dock with the CSM in lunar orbit. Next slide, please. During rendezvous, the pings automatic control the limbs rendezvous with the CSM in lunar orbit. Lunar module descent and ascent engines. The guidance system controlled the descent and ascent engine burns. and the AGs could also control the engines. That's out of board guidance system. The crew, however, had the capability to manually start and stop the descent and ascent burns by pushing their start-stop buttons. The engine thrust control engine arm switch would have to be positioned from off to descent or ascent. So you had to do two functions there. You had to switch this off to ascent or descent, and then of course then you could go to your start or stop buttons. Next slide, please. Saturn V launch vehicle guidance. During the second stage and the S4B third stage, the crew's rotational hand controller was used to generate attitude error signals if the launch vehicle primary guidance failed, which we really never had a case of. Go ahead, next slide. We'll go into the Apollo crewed missions. Okay, Apollo 10. The commander, this was, by the way, this was Tom Stafford. They were coming up from the moon. They were already launched, coming up from the moon. And he inadvertently, he was investigating some, what he thought was an electrical problem. And the crew are in their spacesuits. They have the helmet off and gloves off, but they still have, they're in their suits. He inadvertently hit the stabilization control, that AG switch I talked about. So it knocked it out of attitude hold and put him in that abort mode. So all of a sudden the lunar modules flipped the spacecraft around and end over end, trying to find with the radar system, find the CSM to automatically go rendezvous with it. So basically the limb at that point was out of control. Commander quickly grabbed the hand controller. He didn't know, of course, that he inadvertent what he had done. Switched to manual, jettisoned the limb descent stage, regained control of the lunar module, and successfully completed the rendezvous and docking. So it was another case where having manual capability saved the crew. In this case, it was due to crew error that got him in this situation. Apollos 11, 12, 13, 14, 15, 16, and 17, all but 15. The commander took over automatic control because of hazardous terrain. Next slide, please. Also, during the Apollo 12 for ascent, we actually had a lightning strike, actually two lightning strikes. The lightning strike disconnected all fuel cell, which applies all DC power, main bus power, and also AC power, which caused a loss of onboard computer on board. And the crew was able to mainly regain power and flight control, preventing loss of the mission. Okay, what was that? Back in those days, we had Zener diodes that were in the circuitry. You used some discrete solid state circuitry in those days. And in the case of the motor switches that connected the fuel cells to the main bus and the AC power from the inverters to the AC buses, there was an overload sensor in there that if you had a current overload, it would automatically disconnect. Well, it turns out when you have a sharp negative voltage increase, negative spike on the vehicle, which happened in this particular lightning case, it actually tripped on every NCR we had in the vehicle, which was all of these overload sensors. So that's what tripped all of the DC power and AC power off, was actually tripping those Zener diodes on and disconnecting everything. Now, the reason the crew was able to regain control is we have an entry battery system on the spacecraft that empowered like an emergency bus, not the main bus, emergency bus. But that bus allowed the powering of the manual switches. It allowed the crew to calmly reconnect the fuel cells and reconnect their AC power. And eventually brought things online, even though they had some instrumentation failure, and the crew was able to complete the mission. Apollo 13, you had a service module oxygen tank explosion, resulted in the loss of all the oxygen and electrical power. So you ended up having a complete power down of the command service module and a major power down of the major power. And in order to get back, since the only source of power was the lunar module, the crew had to do a manual crew control of the spacecraft, as you just about had to turn off everything in the lunar module to save the battery power. And a lot of us are familiar with that from the Apollo 13 movie. Just back up just one, the Apollo 14. There we go. Apollo 15. That was that one case I mentioned about, he took over automatic control because he was going to be on automatic, but it turns out it wasn't bringing him into the pre-selected landing area. So he took over control for that reason. Next slide, please. Skylab program. We had 3 manned crew missions Skylab. Skylab 2 mission was unable, after many attempts, to attain CSM docking probe capture. The crew had to use a manual procedure to bypass the capture interlock and manually retract the probe. Okay, prior to Skylab 2, going back to all the way to Apollo 14, when they had problems docking with the lunar module, before that mission, I had developed a procedure because I was always worried. I was responsible for the sequencing system that fires all the pyros, and so I'd worried that what if those little small capture latches really wouldn't make good capture? Is there a way to fire that pyro, retract the probe, and maybe allow the crew to carefully maneuver in and hit those switches around the periphery and still do the hard dock? Well, on Apollo 14, after many attempts, they were able to finally dock, but that took periods of hours and time to do that. In that period of time, I had gotten my procedure, which allowed you to take an onboard connector, cut off the connector, have the wires, and my procedure allowed you to go into the GSE connectors on the lunar docking events controller, and you could insert in the proper pins, which I identified. You could use, like, throw the utility power switch or something and retract that probe. It turns out on Apollo 14, we didn't have to use the procedure. But the procedure got improved later on to where we had a cable on board the spacecraft that would allow you to directly connect up, and you had quick opening fasteners to allow you to get access to that area where the lunar docking events controller was. So we had developed a procedure. If you really had to use that, it'd be much simpler to use. Well, for Skylab 2, it turns out they had to use it. They weren't able to get, and by the way, Skylab 2 was the mission that they had to go up because the workshop was in real trouble with thermal problems, and the crew had to go up there and not only protect the spacecraft there, but also try to get another solar array out. So they basically were going to save Skylab. Anyway, they went to the procedure, which was on board, which allowed you to get out that cable and connect up to the utility power outlet, fire that switch, retract the probe, which it did, and then the commander could carefully go in, which they were able to do, and latch up. And so I basically saved Skylab, plus it allowed the docking of the crew to go in. Skylab 4. This is a little story with it too. Ed Gibson was one of the crew members on that spacecraft, and he was the chairman of the Orion Standing Review Board that we had back early in the program. He was going to be the chairman of that. They pulled a lot of us ex-Apollo people onto that review board as a critical, like, graybeard oversight on the Orion program, and I was one of those on there. And I had written up a listing of all anomalies and lessons learned on Apollo and Skylab and so forth. Ed Gibson was looking at my list. He thought it was real good, but he said, "How come you don't have Skylab 4 down here?" And I says, "Why?" And he says, "I thought we were going to die." I said, "What?" He said, "Yes, I thought we were going to die." And when they were getting ready for reentry, the crew, it turns out the crew procedures, you're on one panel, this is where you get into this human factors thing for manual backups or whatever. On the commander's circuit breaker panel to his left, on that same panel, there's 4 circuit breakers for the stabilization control system. Pitch, yaw, systems A and B, 4 circuit breakers. And located on the same panel close by were 4 circuit breakers. So you had SCS, pitch and yaw A and B. Close by you had SPS, pitch and yaw A and B. The checklist calls out opening up SPS, pitch and yaw circuit breakers because they provided power down to the gimbal motors, and you had to dead fast that before you separated, getting ready for entry, and you separate from the command source module. You had a guillotine come down and cut that. So you didn't want to short out the system. So the procedure calls you out to open up those 4 circuit breakers. Well, guess what? The crew didn't realize it, but they had opened up those 4 SCS A and B breakers instead of the SPS A and B breakers. And after all, it's been almost 3 or 4 months since was the last time the crew were even in the command module, because the last time they were in it when they docked. So you got this long period of time, crew's all suited up. Anyway, so when they did separate, they didn't have the automatic system to bring them around to the proper attitude. As a result, they were apex forward, which meant they would burn up on reentry. If they came in that way, the crew would be lost. So that was the big scare factor for them. Hey, nothing's happening here. We're headed in the wrong direction. But they happened to remember, hey, we got command module RCS control. So they switched that manual switch to manual RCS control, and were, of course, quickly got into the right attitude and came down okay. And then of course, post-flight, they found out, because when the crews went in and looked, they saw the wrong circuit breakers were operated. But there's a lot of lessons learned there associated with training and a lot of things. That's one reason, as some folks know, we on the space shuttle program, you ended up having the crew actually go through like a simulation and do everything and go through all this before you did the reentry. So you weren't, so that would all be refreshed. This is a good example of how you need to do that. And also in terms of labeling of critical functions, location of critical functions, etc. Next slide, please. Apollo-Soyuz Test Project, ASTP. During the second docking, the first docking, Tom Stafford was the commander of that mission. He had 2 rookies with him, Vance Brandt and Deke Slayton. Deke Slayton, you remember, wasn't able to fly earlier, but he finally got rid of his problem, heart problem, or what it was. I can't remember now exactly what that was, but anyway, the docs cleared him, and so he was going to fly on the ASTP mission. Deke Slayton was. He's in the far right seat, which would be docking module pilot. You had the commander, then you had the command module pilot, Vance Brand, in the middle, docking module pilot on the far right, which of course used to be the location of the lunar module pilot. Okay, the plan was ahead of time was Tom would do the first docking with the Soyuz. Went extremely smooth and easy and so forth. He was great at rendezvous and docking. It was also planned that Deke would get to do the manual docking with the docking module, and he would do that. Well, at 100 meters out, he was a little bit off. The docking target was washed out against the Earth background. And even though the docking target was washed out, he kind of pressed on anyway. Okay, then he made contact a little harder than normal. And then after he made contact and he had the contacts closed and connected up, he inadvertently bumped and fired the roll thrusters for 3 seconds. And that caused the Soyuz to really bang around. And matter of fact, the Russians and their Leonov, who was in the commander of the Soyuz, in his book, talks about how they thought they were going to die because they were swinging around so much. It took their docking system to the limits. So they thought they would be done in. Needless to say, nothing was said. However, later on, MCC did apologize. But that was kind of hushed up on the US side. I might pass on though, because of that, the Russians were really concerned about our manual docking. So one time when they were over here during the shuttle program, we were going to be docking with Mir. I had my safety team over and we were over in the simulators, building 16. They were showing him everything that was being done with the laptops and all the things for the manual docking. And the Russians that were with me were extremely concerned. You could see they're very concerned, asking a lot of questions and all that. And then after they left, some of the guys on the simulators would say, why are these Russians so worried or concerned about this manual docking? So I explained to them the ASTP, what happened on ASTP, because you don't ever hear about that hardly. And they said, oh, now we understand. Okay. Okay, next problem. Well, another case where the crew almost killed themselves. Tom Stafford was on this one too. I was in the middle of this one a little bit myself. Is my crew safety crew ops counterpart that was responsible for crew procedures came over to me. We worked closely together and I worked with the MOD guys. And he came over and he said, Gary, Tom Stafford wants to use his Apollo 10 procedures for the Earth landing system. He's not going to follow the later procedures. I had worked very hard. The crew was always worried about barrel switches. Even though we had 2 systems, we had barrel switches in 2 of them in series. In other words, there was no single point failures that could occur on the barrel switches. However, during ascent, of course, early on, those are closed, but you don't have the system armed up. Anyway, the crew were always concerned, even when you're in flight and in vacuum, you name it, they were always concerned about barrel switches. And so as they themselves wouldn't arm up the pyro buses and arm up the Earth landing system till you got down to like 50,000 feet or something, such that if all of a sudden things started in there, they were low enough altitude for the drogue chutes and so forth, they'd be okay. Well, I worked very hard because the system was designed to be automated, that they, enable the system because we really wanted to enable it ahead of time and check it out and verify. And then that way, if the crew passed out or whatever, they'd automatically come in. Anyway, so I asked John to schedule a meeting with Tom Stafford. So I went over and met with Tom and John and I went through and explained to Tom all the changes we'd made to the manual switches. And we did add in redundant contacts on the manual switches, so you couldn't inadvertently control that. And the crew procedures had been changed to keep the pyro buses armed up after command service module SEP earlier, to keep, so that's one function you didn't have to do. And I also argued with him that to go to ELS auto at that point there, and that way the system would be all armed up. Well, Tom, as he left the meeting, said, we're never going to forget to put out the parachutes. You know the old saying, famous last words. Okay, so they come roaring in, and the crews begin to say, and they ended up finally arming up the pyro buses, but that was at that lower altitude. Then they were sitting there calmly waiting, and they got thinking, you know what, we're getting off the low, nothing's happening here. So Vance Brand quickly goes over, he knows we have the manual push button, so he quickly jettisons the apex cover, quickly puts out the drogues parachutes and everything, and it just so happens that altitude they were at, we were doing this all at a very low altitude. The spacecraft was designed such that before your relief valves were open or anything, we always burned off the propellant because you didn't want to land with toxic propellant on board in case you had, cracked open the tank or something else. So you had this automatic sequence to dump propellants overboard, which initially would be firing engines, and then you go to whichever's left over. Well, it turns out what's left over a little bit is N2O4, which is very toxic. So they were low enough altitude when they were on the drogue chutes and all of that, and coming out. And by the way, Tom did suddenly recognize after they were on the drogue chutes, he said, oh, ELS is not in auto. He throws it to auto. Well, then they were at such a low altitude, when he went to auto, the manual parachutes deployed right away. And then once they were on the manual parachutes and everything, they start this propellant dump sequence. And the low enough altitude, the pressure relief valve, which is located on the side of the spacecraft close to Vance Brand, is sucking in propellant fume, N2O propellant fumes. Next slide. Okay, well, I need to finish up here a little bit. Fumes got so bad, Vance Brand pantsed out. Crew was scrambling around to get on their oxygen masks, emergency oxygen masks. They did. Tom quickly put the mask on Vance Brand and brought him around. Anyway, the crew then, of course, finally landed and got picked up. Because of that exposure, though, the crew was in the hospital for 2 weeks when they got back to Hawaii after that flight. They'd been exposed to what was considered lethal levels of N2O4 and so forth. So they were very lucky. At the same time, Deke Slayton was lucky for that himself. They were, of course, doing extensive X-rays of their lungs and so forth for that. And they noted a very, very small place on Deke Slayton's lungs. That was the beginnings of lung cancer. And so he was able to get operated for that right away and was able to live a lot longer. He ended up eventually dying of lung cancer, but that was much later. Matter of fact, he was in charge of the shuttle program who were doing the landing operations out at, with the, where we dropped the shuttle off from the 747 and do those ALT landings out at Edwards and so forth. Deke Slayton was the program manager of that operation out there, you know. Okay, Space Shuttle program. Well, we had great advances in avionics, in design, and of course, a lot more complexity in automation and control functions. We had data buses, MDMs, but we did still keep a lot of manual capability functions on board. They're strictly manual. We had that for landing, docking systems. In other words, you had to manually deploy the landing gear. That was not automatic. Docking system the same way. That was automatic. System management on board, if you had problems, that was all manual. And if you want to reconfigure the automated flight control system in the computers, that was also manual. And our RMS remote manipulator system was mainly operated manually, but there was some automatic modes as well. Next slide, please. The crew did have manual control of the main engine throttles if they had certain anomalies. They had manual control stick steering available for auto guidance flight control system for ascent able and so forth. And of course, you had your standard rudder pedals and all the things for doing a manual crew landing like you do in aircraft. Next slide, please. Also had the capability to manually shut down the SSMEs if need be. And they could also enable and disable automatic shutdown limits if required. And the crew could manually initiate abort stern ascent, which was, as we know, some as the RTLS system. And that could be done by using a abort mode rotary switch and the abort push button. For once again, you had two functions the crew had to do. And the crew could manually command the external tank separation using the external tank separation switch and push button. Once again, you had two functions there, which goes back to that case on Apollo 10, you remember, where you bumped the one switch. Well, if you had two switches, one to arm up that when it was needed and the other, that bumping of the one switch wouldn't have caused that problem. So it's always good when you have this manual capability to have that. Next slide, please. And the manual attitude control was also on operation on board for on orbit. And of course, we had a station at the back where you could operate from back there. Next slide, please. Okay, during the STS-9 landing, John Young was the commander, and the pilot slipped my mind, and Brewster Shaw was the pilot. Okay, and we'd had I need to back up a little bit because on orbit we actually had a general purpose computer 2 failed on orbit. Well, no, wait a minute. We had a computer fail on orbit, a hard failure. And it had to, and then we had to turn it off. It turns out she actually had a short in one of the chips and memory system, I think, or something on the computer. And then shortly after that, she actually had another GPC fail, but they were able to recover that one. So because one GPC had failed, okay, they had to do this reconfiguration of the avionics chains, the 4 strings of avionics, on which computers were on which string and so forth. Okay. But then during landing, that GPC that had been recovered on orbit did hard fail. right there when they were landing. And so the pilot, Rooster, went through a reconfiguration for that. The problem here is he was going through his normal reconfiguration, forgetting that that normal configuration had been changed on orbit. So in actuality, he caused a complete loss of flight control during that reconfiguration. And here's a case where the crew had no visual displays of what that configuration was. In other words, he would have had to remember what he did back there on orbit. Now, fortunately for the crew, they were already had landed. Okay, they were on the main gear was down and everything. So the loss of control wasn't that big a deal, and there wasn't a lot said about it beyond the mission. It did result in developing cards, display cards for the crew, that if you ever did a configuration on orbit, you had those things on the panel right next to you. So if this situation ever occurred later, you knew exactly which configuration you had to go to. So they used cue cards. But this is a good example of this not having the right sensors back to the crew on system configuration in order to be quick, in order to quickly be able to get your control back. STS-32. Here's a case, not Vance Brand. I'm sorry.
Dan Brandenstein.
There you go. Great, thanks. Dan Brandenstein. And you know, as you get on in age, those times go. I used to have all those guys. Matter of fact, all these people we're talking about, I know very well, especially John Young. And Dan Brandenstein went to our church and everything. But anyway, Dan was the commander of that mission. Crew was asleep. We're on orbit. And the INCO at that time, they were going to have to send up a state vector to the shuttle, and they're getting close to LOS. And you had to do it in AOS or LOS. And so he sent up the command. The shuttle rejected the command, which was the right thing to do because the command had gotten garbaged since it was close to LOS. So a signal came back that it had been rejected. INCO forced it to go in. Well, that immediately, you had a case where the spacecraft thought you're flying around the center of the Earth, whatever. But anyway, the vehicle went into a spin. Fortunately, we were on vernier controls. If we'd have been on the primary RCS, this mission would have been a goner right away. On verniers, it started spinning up. And we uplinked quickly to get the crew awake. And they got awake, and Dan got awake, but they were really tumbling. And so he got up and got control of the spacecraft, but they were getting close to this stage where centrifugal forces and etc. would have almost caused them to lose it. So I won't mention his name. I know who that INCO was because at that particular time, I was still working over, I think, in flight operations at that time. I can't remember now. But I know who that was. But anyway, needless to say, he never was on console again. Next slide. STS-3. Final transition, and this was a case, it was taken, we were going to be doing it for the first time out our backup landing area in New Mexico. But at the same time, we were wanting to try and do auto land, to stay in auto land as long as we could to see about that capability. Well, the final transition from autopilot to crew manual control was delayed to test the automatic landing system over what you'd normally do. This late transition did not allow the commander sufficient time to become familiar with the vehicle handling characteristics prior to landing, which involves relatively complex flare, derotation maneuvers. Additionally, the landing occurred at the alternate landing site in Texas, which is higher altitude, having lower atmospheric pressure and drag. This resulted in a hard, fast landing and actually having the vehicle get into what we call PIO, pilot-induced oscillation, up and down while it's landing. During approach on STS-37, the commander, and this was Steve Nagel, which I know real well. The other was Joe Engel for 3. I believe was Joe Engel for 3. I can't remember now. Steve Nagel was 37. He misinterpreted the indication of low energy around the hack as high energy. And the high winds at low altitude resulted in a low energy landing that was 623 feet short of the runway threshold. Okay, so here's the case of pilot error. Needless to say, unfortunately, Steve is a great guy. I know him well. Unfortunately, he didn't fly again. STS-90 manual control during landing resulted in a hard, fast landing due to human factors and road wind gusts. Okay, next slide, please. Okay, there was also a number of cases that were really not documented, but you know, if you ever bump the hand controllers or so forth, you automatically got out of automatic. So there's often cases that occurred where they were inadvertently bumped. The crew quickly recognized it and were able to get back. And so there was really not many functions, but the crews will tell you that often inadvertently happened. And then for many of the functions, as I mentioned, control was manual. All landing is dockings to the mirror and to the ISS were all done manually. And of course, like I mentioned before, landing gear, drag chute deployment, etc. Next slide, please. Okay. I might point out here that I've got a report that covers all this that I developed there. I think I mentioned at the beginning was developed back when the commercial guys were coming around. And that report, by the way, which I could send as Vanna to send out to whoever would like to have it. The reason I mention that now, I cover the Soyuz, the Russian spacecraft, the early Vostoks, Vashus. I talk about their manual capability and automatic capability in that one report. So you get a discussion about all that as well as what I covered for US. The US is covered here for lack of my time, because as you know, I spent a lot of time expounding beyond the charts from personal experience on these anomaly situations. We're a little bit past the hour, but let me go through this chart because it's a great summary if you wanted to glance at something. First, you need to understand what's mentioned at the bottom. You have a check mark if you had manual capability. And by that check mark, if the manual capability was used for normal operations, you had an N, or if it was used for strictly contingency, in other words, then you had a C. And then, of course, you had an X where manual capability is not provided. And yes, you'll notice that on Soyuz, they did not have near the manual capability we've had on our spacecraft. And so it mainly dealt with the abort situation and attitude control. And in this case, you're at abort initiation on the contingency. This particular contingency was ground command, not crew. They still, to this day, they still don't have manual capability. And of course, they do for attitude control, and they do for their burns and rendezvous. And of course, as we well know, for docking and undocking. And of course, they have an automatic system for docking and undocking. That's the reason you have both a C and an N there. And then as you can see on the case of Mercury and Gemini, places where you didn't have the manual for those vehicles. And then as you can see for Apollo, you pretty much have coverage all the way down. And then of course, Space Shuttle, and then the Space Shuttle of course covers this unique landing stuff. Okay, I ran a little over on time, but I'm open for questions and answers. So well, that face looks familiar. Good morning, Bonnie.
Good morning. So Dan was the commander. Well, I can share with you what it was like on the vehicle.
Great. We'd like to hear from you.
Well, anytime you hear a master alarm in the middle of the night, it does wake you up. And I think the first thing, I was down sleeping on the middeck and asked Dan what was going on. And he says, well, the moon seems to be orbiting our vehicle. As you recall, there was a big moon out that night, but it got recovered pretty quickly once he got control of the vehicle.
Great.
Hey, Gary.
Really good to see you and hear from you. And Bonnie knows all about these Soyuz.
Gary, thank you for such a great presentation. I was looking at your table 1, the summary of manual controls and capabilities by program, and I couldn't help myself to think that there's at least one more or maybe 2 more columns need to be added now, because since we have a commercial capabilities and commercial vehicles are flying, hopefully no contingency, or at least not known yet, but the capabilities, it definitely can be updated. And in addition to that, we need to add the gateway as a program in a few years when we start flying it.
Okay, let me bring up just one thing here and share the
Sure.
screen.
Do you want to share?
Yeah,
Hold on. Yes.
Okay, I'll bring it.
You should be able to share right now.
What this is, that's a report I was talking about. And as you can see, it was developed way back in 2013.
You're not sharing it.
Oh, I'm sorry.
Gary. At least we don't see it.
Share. Okay, I'm sorry.
Perfect.
Okay.
Yes.
As you can see, this developed back in 2013. It was back at this time we were talking a lot about the commercial vehicles coming on. And there was a lot of concern from the crew office as well, because they were hearing lots of words about this automation and everything. So that's when we developed this report, and this presentation is from that report. And also, just since we've started flying the commercial vehicles, all of a sudden the crew office and SpaceX themselves had gotten always a lot of questions about the manual capability. The Boeing, I think the Boeing spacecraft has a little bit more manual capability than the SpaceX. However, both are pretty automated. And so the request for me to some of the folks had come across this manual report. The crew officer was aware of my report and indicated, and so I got a request from SpaceX to actually give them a presentation, which was given early December, just last year, early December. And it's a presentation I just went through now. And because they've been wanting to, needed to take a look at this and, see what needs to be done. I pointed out, I felt like a couple of things. One is for abort functions for ascent. I almost felt like that the crew must have manual capability, because Bonnie's probably heard about this and knows about it too. The Russians had a case where they had a crew on board on the pad and they had a fire on the launch vehicle, and the fire actually burned through the wiring that would send the automatic signal from the launch vehicle to the spacecraft. And fortunately, the ground command was able to send the command and get the command in time to abort the Soyuz crew off the pad and save them. So, and the crew, by the way, was fully aware they had a really bad problem, but they were sitting there in the situation, there's nothing they could do about it, and you had to depend on the ground crew. Okay, well, I'll let you go back here.
You need to stop sharing.
Okay, let's see, how do I stop sharing? Oh, stop sharing, there it is.
Right.
Thank you.
Great. Any other questions? The floor is open. I see, if you don't mind, I can read at least one question. There's a thank you for Andrew for a presentation and for your service to the space program, Gary. And then Bonnie also thanked you for the many years of serving human spaceflight safety. I can add to what Bonnie said, is that I have a privilege of working on Gateway program. And when you were talking about GPCs, that's exactly what we're going through with the crew office, working on design of the crew displays and functionality of GPCs, because that will be a main interface for crew with the various systems of the Gateway. So it's extremely important, timely, and I am glad that we are recording it, because I will definitely recommend to my team to listen and review your slides, and perhaps they even will reach out to you for additional questions, information, because again, we should not forget what the knowledge that we have accumulated with many years of working in various programs, and we can use that knowledge instead of reinventing the wheel.
Okay. By the way, if you like, I can send you that report. So if others that listen to this want to.
Absolutely. Mm-hmm.
Okay.
Hey, I have a question, please. It's Bernie Rosenbaum, Gary.
Yeah.
Hey.
Oh, hello there.
Yeah, I spent 50 years there at NASA, starting in '63, and I was working at Gemini, and you mentioned Gemini 8. And as I'm sure you're aware, the problem there was that we had a short somewhere in the ground wire, and for some reason.
Well, it turns out you had a stud-mounted diode in the circuit for firing the jet, and that shorted to ground. Back in those days, in the control systems, you'd short the ground to turn something on. You had to short the ground on that, and that caused the firing of that. That's the best they were able to determine later on, is probably what caused the short, because they had problems with those diodes that were stud mounted, that if you wasn't careful, you could break down and short. But it was a hard short, you're right.
Yeah, and on that one, I thought Gemini was unique, where they were shorting the ground side as opposed to control the thrusters on and off, as opposed to the power side. Well,
they were, but here's a case where that short to ground was like a command to
right. I understand that. What I'm wondering or asking is, what was the rationale on controlling the thing from the ground side as opposed to from the power supply side?
It was, in those days, it strictly had to do with the capability of the solid state devices at the time. They couldn't operate at the higher voltages. So you always had them in the ground side. Now, that's not true nowadays. Don't get me wrong. That's not true nowadays. Now, at the same time, the Russians will tell you, we don't have shorts in the wiring or so forth. And that's because they don't use a single point ground system, okay? They always have a power in return. So to be able to inadvertently operate on the Soyuz, you got to basically have 2 wire shorts. You got to be able to short the power. In other words, if they have something short the ground, that won't fire anything because you got to short the power return. So the Russians kind of have additional level of redundancy in the wiring that we don't have.
Okay, so there's
Now,
a switch on both.
that's done for EMI reasons. We do it because single point ground system is much better for reducing requirements of EMI, and then using but that sets you up for the case where you can have shorts to ground. Now they do have their ground power return tied in the structure by a high resistance resistor. Okay, a high resistance resistor. That's done to bleed off any sort of, electrostatic function.
Okay.
But I was fairly impressed when I first heard about that way back during the Apollo Soyuz program. I thought, well, that is a pretty good deal that they got this, power. They have their returns isolated from structure.
Okay, but you're saying on the Soyuz, they have a switch both on the power side and on the ground side, both of which have to close to turn the thruster on.
They could, but at the same time, if you're controlling that from a box that's got that power return also in that box, then you just, of course, have to switch the power side. But you're right that you got to have both power and return.
Okay. Yeah, that would give you some additional reliability of a false turn on. That's for sure.
Yeah.
But it doubles the chances of something failing too, because you have to have both of them on to turn on.
Right. So, and of course they have 2 systems usually, 2 or 3.
All right, but excellent talk. I mean, you obviously spent a lot of time putting this together. Did SpaceX really jump into a lot of this stuff and take your recommendations at heart, what you were talking about?
I had questions, several questions. One is they wanted to know what I thought about SpaceX, and I told them I was very well impressed with them, mainly because I was really impressed with the amount of testing they do on everything. Mm-hmm. They don't depend a lot on analysis. They do much testing, as we know. They have no problem blowing up a launch vehicle during the early testing phases because they feel like you learn something from that and so forth. And I think that's very good. They and I told them in the case of the automation stuff, it's important to have the redundancy in the quality assurance with that system. And I pointed out, of course, for selected areas, it's important to maybe have manual capability, but you got to follow those rules I had at the beginning, making sure, if you're going to implement it, you follow the correct things.
Yeah, a lot of history there.
I have a question. It seems to me that a gross missing item from your presentation is the Apollo 1 fire. And at the time I was working for North American Aviation, not on the Apollo program, but it's from that disaster that caused me to be drafted into the Apollo program to do some calculations on the geometry for the whole mission. But I was wondering, from your standpoint, Gary, do you have any thoughts about the Apollo 1 fire and how that influenced the rest of the space program and how they approached risks of failure from that standpoint? And specifically on that mission, on that disaster, was there anything in your mind that could have been done to avoid a disaster like some kind of automatic release of the hatch, so the astronauts could possibly escape if there was some kind of disaster in the capsule?
Well, I was in Mission Control Center in Houston on the EPS console in the SSR when the Apollo 1 fire occurred. Back in the very early days, engineers would actually sit alongside their flight control counterparts in the MCC. And in this case, we're monitoring the test. And the failure occurred about 6:30 Cape time, is 5:30 Houston time. About 5 o'clock, Kranz and most of the flight control team had been released. After all, JSC was just in a monitor mode for the Cape was involved in the test. So the flight control counterpart that was sitting with me on the EPS control console left. I was still there because I was there following the data and the systems, being responsible for power distribution and so forth. So myself and Mort Silver was a North American ECS flight controller. He was on the ECS console and I was on the EPS consoles. We were the only ones in the SSR when the fire occurred. Chris Kraft was still out front, and he did have other MOCR people out there with him. And he come, and of course, it gets to be hard to talk about because I was there on console when this all happened. Chris Kraft come running back to the SSR and said, "We're going to be playing back the data. We want you to carefully go back through this data to see if you can identify what was close to the time of the fire." And so I was there all night long looking at data. I did note that the time the crew hollered fire, that we had a short on both main bus A and B at the same time. What that told me is that short that occurred that caused the ignition of the fire had to be a diode load, which would reduce the number. So later that next day, when I went back to the office, I spent my whole time going through trying to identify and write down and list all functions or anything that was powered from both main bus A and B. And I had that list. And then and by the way, when I was on console still there, you knew the crew were in suits. And of course, being pretty naive, I guess, I was thinking, well, the suits and the crew are in their suits, they'll be okay, thinking that. And then of course I heard the test director at the Cape come on and told Chris Kraft to go to a private line. And of course I knew that that was bad news. And Chris had announced on the loops, of course, that the building was being locked up. Everybody was not allowed to leave. And we could make one call to our wives to let them know, and not say what it was, but just say we weren't going to be home, which I did. It turns out my wife had already heard on the news, but I didn't say anything. And then the next week I went down for the investigation. I was sent down there, and I was the one engineer charged, along with a photographer, to go inside the spacecraft and actually in the command module. And of course the seats and all the stuff had been taken out, but and had been destacked from the pad. Actually, I was out at the pad just before that. So I was at pad 34 to see it, but we didn't go in the capsule at that time. But then I was charged with going through it all and locating. Now it turns out, and I've got some of the folks, Savannah and others have heard my presentations on a Apollo 1 fire, and I could even show you location and equipment, lower equipment bay, which we've determined is the most likely source of the fire. For some strange reason, maybe not strange, but they don't show that in the reports. So I've got a photograph of boilerplate 14, which was built just like 12, and was going to be the next spacecraft coming along, spacecraft 14. And I've got a picture of that area, and I know. And it turns out there was a diode load that was powering the environmental control system, ECS. It is over in the left-hand equipment bay. Now that particular area down the lower left-hand equipment bay, that was all gone. When you have an oxygen fire at that high level, you burn aluminum, you burn metal, you burn everything. So you didn't have anything to look at there. So it was part of my investigation of that area. I did go through all the other. And most of the other areas, by the way, if you wiped off this smoke soot, it was, pristine condition underneath. In other words, there was actually very little damage elsewhere around the vehicle other than that area around the ECS. That area. But we were able to look at closeout photographs of that area, because they always took closeout photographs late. And there was a wire going over this is an area just below Gus Grissom's couch. And it was wrapped, and it had a Teflon overwrap over the Teflon wiring that kind of protected, and it also went under a door that can be opened and closed in these ECS area. The last closeout photograph of that area showed that Teflon overwrap had slipped down and was no longer protecting that twisted power return pair of diode power to there. And at that time this occurred, Gus was trying to change his COM connector, change out the COM connection because they were having communications problem. Well, simulation showed on the ground that if you're suited and you want to try to do that, you got to swing your left leg off the couch and step down on the floor in that area to twist around and make that connection. So, it's just me saying, and you won't find that in the reports, but I think he stepped right on that wire. And of course, he's in a boot. For sensitivity reasons for the Grissom family and so forth, you don't, that's not mentioned. And you won't see, but I do show and talk about, at least talk about that, how we determined that as being the ignition source.
Well, thanks, Gary. And my question was also about.
Okay, what could we have done? Well, the first thing was materials inside. They actually had foam pads on the down below the couches. They used to protect the flooring and the equipment. And there was no. So corrective actions we did for the future. We had metal hard covers over all external wiring. And you had a flooring, a hard flooring that could be put in a matrix fashion in there for workmen and so forth. And we should have never been, of course, at 16 PSI when you had materials. Materials were only certified at 5 PSI, but we had a lot of materials in there that weren't even like that foam. A lot of things not certified for that. Jerry Goodman, who was a crew engineer at the time, was actually complaining before the fire that the crew was putting too much Velcro in the spacecraft because Velcro was a concern. There was a limitation in where that was placed and so forth. And the crews liked it because you'd stick things to it. And they were putting that in a lot of places. And he was concerned about that from that flammability standpoint. So you had a case where you didn't have materials compatibility. You didn't recognize the test at pure oxygen as being hazardous. I also have in my discussions and report about a fire that occurred almost a year before that I got called in to investigate. There was an oxygen fire, and that report was classified. So you never got to hear the results of it. And I think, that should have been a wake-up call for oxygen fires are hazardous. It was a qualification fire in the environmental control system out at Torrance, California, at the vendor there that designed the air research, Torrance Facility Air Research, that designed the ECS system. That was all hushed up when they had the fire in that chamber. That was at 5 PSI because that's what the spacecraft was being at. And I got notified and sent out there to investigate that. And so I was in talking, and it turns out in reviewing all the data, the thing that was done just before the fire and the blowing open of the chamber that they had this in was the guy turning up the variac on the ECS duct heater. And in investigating that, I was talking to, it turns out instrumentation engineer was in charge of the test. By the way, there was no engineering analysis or materials compatibility analysis of this test either. The guy in charge of the electrical stuff was electrical technician. And when he was trying to come up with how to do the ECS duct heater, he went down to Sears and bought one of these heater tapes that you wrap around your hot water line, your cold water lines outside to keep them from freezing. So it was designed to be operated on a cold water line in cold weather, okay, that insulation capability. You took that same wiring and wrapped it around an insulation duct with insulation around that and put it in a vacuum of 5 PSI pure oxygen. So when you turned on that heater, you were trapping not only heater against that duct, you were heating up that insulation. So you heated the temperature up, and there was evidence that the insulation had failed on that heater tape, and that caused failure. And by the way, when I wrote up my report on the what the cause of the ignition point was and so forth and all about it, and all my data to back up what I was saying, they didn't allow me to say anything about the tech going to buy the heater tape, okay? And by the way, that didn't show up in any press, anything. It's unfortunate both Rockwell and NASA put the lid on that thing, didn't want to show they had a failure, I guess. Anyway, the other thing is kind of shocking. Here I was involved in the investigation. I was not a part of the Rockwell NASA investigation board. I turned in my report to them. I never saw the final report. I never saw the final report or get a copy of the final report. It's not distributed. And I reconstructed the information for lessons learned in the report in later years, because when he got back, we had to write trip reports. I basically had all of my information I turned into them in my trip report that I had sent, to my managers and so forth, showing what I'd done. So I used that information to put together. But when I was putting the information together for my report on that investigation, when I was working there for SAS Flight Safety Office, I called up Hank Rotter and some of the guys and I said, did they know anything about it? And they said, no, but I tell you what, there's an ECS library over on site in their building, and he would see if they couldn't find, and sure enough. So what was it? 4 or 5 years ago, I finally got to see the actual report, official NASA investigation report. So the first time I ever saw what they even put in there about my report. They did identify what I determined it to be, a short in the duct heater. Didn't say much more about it. They also implied that because, and they did initiate actions to make sure we had circuit protection devices in case of a short and overload, they would disconnect and trip. But there was no like kicking off an investigation of what did materials compatibility have to do with this? Is oxygen a hazardous test? Matter of fact, the bottom line of the report implied, well, since this was really a non-flight hardware that failed, well, they basically indicated they thought they were okay. So, I have concerns that, and my lessons learned out of that is how investigative reports should not be classified and so forth. You need to be open about that sort of stuff. Well, I've given folks a lot more. And believe me, a lot of these stories I used to tell is what led to the lessons learned report that some folks have seen. I've got it's titled 50, Gary Johnson, 50 plus years of human spacecraft. The only regret about a report is they didn't put in anything in there about the Shuttle Mir program or the ISS. So they limited me to just covering like Apollo, Skylab, ASTP, some of the early space shuttle design. They wanted to limit the time it took to put the report out and the size of it. And the report didn't have any photographs or pictures in it. I've gotten a lot of great feedback from the report though, the George Abbeys. Matter of fact, Gerstemeyer sent me a lot of stuff, good information back. A lot of people have reviewed it and given me good reviews on it. So.
Well, thank you, Gary. I appreciate that information. I can tell you from working at North American Aviation at that time that it was, of course, a devastating blow for the company on that incident. But after a year or two and maybe a little more years, they looked at it as a silver lining for the whole space program in that it made us concentrate on errors and safety a lot more than it used to be. And the feeling, of course, from their point of view, is that it probably saved some disasters in the future because it was a lot more concentration on what could go wrong that wasn't considered before.
Right, and that's what also led us to having these design manager walkthrough inspections of every spacecraft before we shipped it to the Cape. And I was the one that went through all of those spacecraft to check and verify the wiring was okay. And we did that on the orbiters for Space Shuttle. Because right after Apollo fire, we had a center design requirements that any spacecraft managed by JSC, you needed to have these walkthrough inspections before, and we had these ADA design stamps. Unfortunately, that wasn't applied to space station. And the reason was that was managed out of headquarters. And even though I raised a big issue about that and so forth, and about what that helped us on the other programs, they turned all that down. And probably would have prevented having one of our ISS radiators up there that's not quite as efficient as the other one because it was connected up wrong. Because one thing that the inspections did was, that was, by the way, the first time our NASA Rockwell engineers got to look at the spacecraft too. There was a union, I was shocked to find out in those early days that there's a union requirement that I could go down there as a NASA person on the manufacturing floor and look at some of the hardware and stuff and look at that. The design engineers were not allowed down on the manufacturing floor. So when we had these walkthrough inspections, we'd have the Rockwell designer as well. And this one case of having the walk around inspection on Columbia before we shipped to the Cape probably saved Columbia for any future flight. Because it wasn't me that found it, but the Rockwell thermal guy was going through doing, we had all these teams doing the inspection. He was looking at the installation of the water lines going from the forward compartment to the aft compartment. And he noticed they were mounted directly to structure. And they were supposed to be on insulated standoffs because there was a heater mounted on the lines, but obviously not very good if you're trying to heat up the whole orbiter instead of the line. So he was able to flag, and they caught that and corrected it. Now you say, how come quality assurance didn't catch that? Now, a lot of people may not realize quality assurance inspects to the manufacturer's installation drawings, okay, to make sure it's installed correctly to the manufacturer's installation drawing. They don't inspect for the design. So if, you know, all the quality assurance folks did was ensure that that was mounted to structure, okay? So there's evidence there of how this letting the designers look at the actual hardware saved us for that particular case. But not allowed
Gary,
to do that
that's,
on
and
ISS.
what we are using right now approach is verification and validation. So what quality assurance is essentially did or have done is the verification. It's if it's implemented according to requirements, and validation is if it's designed and performed to the way that it's expected.
That's good.
And that's where you would be checking for additional, whether it's implementation to what's needed, or it's something that is absolutely not going to be used, or if there's hazards that have been introduced with the implementation.
Yeah, okay. Well, I'm way over. Sorry about that.
That's
Well,
all right. We always happy to have you, and we really don't have a limit. I like to be to stay conscious for the other people's time constraints. I wanted to real quickly plug in for our next Saturday. We will have Kumar Krishan coming with with presentation on inspiration, imagination, inclusion, and leadership for a great future. And so that will be for our diversity effort within our section, and everyone is obviously welcome to join us. I will send the description of this presentation via our voice of communication, both through AAA Houston mailing list, mailing distribution, as well as Engage, AAA Engage. So whichever way you have received the announcement about this presentation, you most likely will get the next one. Otherwise, Gary, you are welcome to answer as many questions as our attendees have. And for our attendees, for those that are not frequent attendees, Gary attends, relatively speaking, frequently. And in our informal interaction, he answers and provides many stories, just like what you heard right now. Gary, your floor again.
Yeah, somebody did have a question about the Saturn V manual control option because he came in late. But yes, we did have, but it was for second stage and third stage of the Saturn V, not first stage. Don Edberg, I think, asked that question. Yeah.
Yes.
Thanks very much for all the thank yous I got. Yeah, I was following the EDA, being responsible for the emergency detection system. I did have some interfaces with the Marshall Saturn V folks. And I had a chance to be at the spacecraft level at the pad prior to Apollo 8's launch on Saturn V. Never got to see an Apollo launch, so other than the board testing we did out at White Sands. I was always at the mission evaluation room back in Houston.
Well, thank you everyone
Okay,
for
thank you.
joining us. Thank you, Gary. I always feel special because you have joined us and you have so much to share and so many stories to share and knowledge to transfer. I wish we can just plug in some sort of a external
you'll
drive
get bored.
and upload it.
You'll get bored quick.
Right. Anyway, okay, well, thank you, everyone. Thank you very much. Have a great week, and we'll see you
Okay,
next
thank you.
Saturday. Thank you for
Thank you.
joining.